Yeah, so welcome to those who have joined us last Saturday. Welcome back. And those who are new to Research Insider, welcome again. I'm Apple. I'm doing my PhD in University of Edinburgh in molecular plant science. So this science chat is co-organized by MBios, Malaysian bioscience scholars, 100 scientists in Malaysia, and our media partner, which is Science Media Center in Malaysia. And welcome, Stanley. Over to you. If you can share your screen now.
Yep. All right. So yeah, first of all, thank you, Apple and Research Insider, for inviting me to share a little bit about myself and my research project. So yep. So first of all, I'm Stanley. I'm a first-year PhD student in University of Bristol, and I'm part of the COMET group, which is the Center of Monitoring and Observing volcanoes, earthquakes, and tectonics. So basically we look at, we monitor things globally, especially like volcanoes, earthquakes, and mountain building events, stuff like that. And my study is being funded by the Leverhulme Trust. And I'll just share a little bit about myself. So first of all, I did my SPM and A levels in Sarawak. So basically I've just lived my whole life there until I moved to the UK 5 years ago for my undergraduate master's degree in geology in Bristol as well. And I decided to stay on in Bristol because I think it's just a great place to study whatever I'm studying, like volcanoes and stuff. So yeah, so this background over here, you could see that it's a volcano, and then there's lava lake around here. And this volcano itself is actually quite famous recently due to its eruption in 2017. And this volcano itself, I think you would recognize this place. So this place, I'm pretty sure like most Malaysians would know where this is as well, because this on the foreground, this is the Stairways to Heaven, and the background, this volcano itself, is this volcano, and that's the Agung volcano, and this is situated in Bali, Indonesia. And things are really great. It looks amazing and it looks really cool as well. But things get pretty scary and devastating when it erupts. So you could see like the difference, like, I mean, it's really cool to see volcano erupting, but the consequences and the risks, the hazards that's being involved with it is just quite scary. So first of all, before going into volcanoes, I think I'd like to say how blessed we are as Malaysians. Just being born in Malaysia itself is just such a blessing. So you can see like the typhoons that's going on like around here and just doesn't pass through Malaysia. The earthquakes as well surrounding Malaysia. And I mean, there's a few earthquakes going on, but it's not that devastating. So basically, in other words, we're just really blessed to be born in Malaysia. And this is true as well for volcanoes. So over here, you can see the volcanoes that's surrounding Malaysia as well. And there's definitely some in Philippines as well, in New Guinea. And as of the 4th of June, there's 44 volcanoes that are currently erupting. And in Southeast Asia region itself, there are like 991 volcanoes that are active or and potentially active as well. So it's pretty scary, but it just shows how blessed we are. So how do geologists or volcanologists monitor volcanoes? So first of all, you could have like personnel going to the ground to measure things. So you can measure deformation using tilt meter, GPS, or surveying, or you could look at gas emissions by volcanoes as well. And you could measure like earthquakes or what's really going on, like tremors going on underground using seismometers. And lastly, you could use satellite techniques as well, or remote sensing techniques to monitor volcanoes. So remote sensing technique itself, it's basically measuring things or sensing things remotely, hence the term remote sensing. And for my study, I'll be using satellite techniques just because it's much more readily available at volcanoes that's really hard to get to. And the reason we use satellite techniques because ground-based monitoring techniques may not be readily available, and to have like ground-based networks itself is quite costly and it's not readily available at most potentially active volcanoes. And one good thing about satellite techniques as well, it's not too expensive, and as the old Malaysians like, some of them are free as well. So first of all, how do we measure volcanic deformation using satellite techniques? So first of all, when magma intrudes to a magma reservoir, you could imagine like a balloon blowing up or expanding. And as the balloon expands, the surface deformation that's being observed over here inflates. Or if the magma withdraw, the volcano inflates. And these surface deformation can be observed using satellite techniques. And in this case, we could measure the surface change using INSAR technique, which is interferometric synthetic aperture radar. And basically it's a technique that measures the elevation of the volcano using radar waves. And this is basically the waves, and as the satellite circles around the globe, and then the phase changes over here, the phase changes measures the surface displacement of the volcano. So the phase changes over here can be interpreted as how much displacement has gone through between the 2 dates of the satellite passing through the volcano. And these surface changes can be observed as these rainbow fringes over here. And these rainbow fringes shows how much that's being displaced when the magma intrudes or withdraw. So that's volcanic deformation. And for gas emissions, we could measure sulfur dioxide gas emissions using spectrometer on board of the satellite missions. So this is how much gas, how much SO2 gas that's being released on the 27th of November during the eruption of Agung. And then basically what these gas emissions mean is that it may be linked to there's more gas because it's going to erupt, or if like there's less gas that's coming out, it means that the volcano may be erupting soon because as the reservoir that's being clogged up, it's like the bubbles can't come out. So this is volcanic degassing. So how are these two linked together? So first of all, these techniques are often treated as individual observations when volcanic processes itself are fundamentally linked. So because it's like a natural processes, so everything is linked together. But these observations are, as of now, are often treated independently. So what we know so far is that subsurface volume change can be measured using INSAR techniques, inferred from surface displacement, and the amount of gas that's being emitted can be measured using spectrometer, and the gas emissions can be used to understand the magma properties underneath a volcano. So to understand like how magma evolves from like a deep reservoir or a huge depth to a shallow reservoir, we first have to understand like what's really going on to the thermodynamics of the magma during magma ascent or decompression. So how are these linked? So first of all, we could use thermodynamic models to simulate magma evolution. So first of all, you could imagine that there's like H2O, CO2 content in the melt. Like you could imagine like in a cup of water, if you add some sugar, there's dissolved sugar. And then as you reduce the pressure or as you decompress, these volatiles to exsolve. So these volatiles that's being exsolved from the melt increase the amount of volatiles in gas phase. So this gas phase basically means that there's more gas bubbles in the magma itself. So with this, you could in a way estimate how much gas, and in this case, we're measuring how much SO2 that's being trapped in the magma itself. And with all of these gas, with all of these exhaust volatiles as well, you could estimate how much exhaust gas are there in the magma. So because density itself, it's related to gas. So basically, you could imagine like when there's more gas and gas bubble expands, the density of the material would reduce for a fixed amount of volume. So basically, it means that the bulk density of magma decrease as there's more gas being exhausted. And because magma compressibility itself, it's linked to the bulk density of magma through the pressure gradient and the density gradient of the magma. So basically it means that the magma compressibility increase as you decrease the depth. And that means the normalized volume change, which we define as the amount of volume change in the reservoir over the amount of volume that's being erupted from the eruption. And that with that, you could infer the surface displacement that's being observed at the surface. So basically, if the magma reservoir is at about 3.64 kilometers, you could infer there's a volume change at about, say, about 4 meters over here. So all of these are just simulations, and so all of these are not real data. It's just simulations. So from here you could see that the normalized SO2 can be measured using spectrometer, and the surface displacement can be measured using INSAR. So by using these two parameters, you could, in a way, understand what's really going on for the magma properties prior to eruption. So from this, what we know so far is that the presence of volatile would make the magma more compressible, so that if there's more gas, the magma is much more compressible. And if there's higher compressibility, it means that the ground deformation itself would be muted. So you could imagine, like, here's a piece of rock. Yes, geologists have rocks in their room, and here's a sponge. So you can imagine, like, because for an incompressible magma, if it intrudes the magma reservoir, the surface displacement that you can observe, it's directly reflected. So the amount of volume that's being added can be observed directly onto the surface. Whereas if it's a sponge, if it's a compressible magma, whatever observation you see on the surface, it's not directly being observed, just because the magma itself is compressible enough. So that means the amount of surface deformation that you can observe, it's not directly reflecting how much volume is being intruded into the reservoir. So this study is built upon a framework by McCormick-Kilbride, and so from here we could see that he defined that the explosive eruptions tend to have closed volcanic systems, and because explosive eruptions happen so quickly, we would say that we could assume that there's no gas, there's no extra gas that's being exhausted. So say if the volcano erupts at, say, 3.64 kilometers, we would, in a way, we would expect that there'll be about 7 kilograms per meters cube of normalized SO2. And from here, we could see that by comparing different kind of volcanoes and with different kind of parameters, you could see that in normalized volume change and in normalized SO2, it's quite different among a range of volcanoes with different magma properties and different kind of parameters. So my research project at the moment is trying to understand how does different volatile contents in the melt could affect the compressibility, and how does it affect the normalized volume change, and how much gas would be emitted eventually. So that's all I have to share for my project at the moment. But before I finish, I'd like to share a little bit about why do we study volcanoes? Like, why do we care about this? Especially like for most Malaysians, I think we don't really care about natural hazards at all because we don't really experience that. So this is a lava that's flowing in Kilauea in 2010, and you can see like how slow a lava could flow. And for most of the time, you think that yeah, I can just run away from this. It's just so slow, and in fact, you could actually, like, if you want to, you could step on it. And however, things could change if it's less viscous, and if there's like continuous magma supply. from the source. So in this case, you can see that these lava flows are actually flowing like how river flows actually. Like these are what you would know as like rocks when it cools down. So you could see like these rocks flow, so like rivers. So it shows that how fast things could be and how dangerous things could be. And this is an eruption, not eruption, a pyroclastic flow in Mount Unzen in 1991, and just shows that like how dangerous things could be that's being associated to volcanic hazards and risks. So yeah, well, the good news is the man survived, yes, because luckily the pyroclastic flow did not reach the guy that's taking this video. So things are quite scary with all of these volcanic hazards. And to put things into perspective, because this itself is quite far away. Oops. Yeah, things are really, really scary, and it just shows like how, well, magnificent, but at the same time devastating as well. So this is the 2018 volcanic eruption in Fuego in Guatemala. And you could see that these flows can reach up to 700 kilometers per hour. So that's like way faster than whatever speed you're driving in your car. And these temperatures of these gases ranges between 200 to 700 degrees Celsius. So basically, if you're in this cloud or in this ash, basically you either die of suffocation because of all of these gases or ashes, or you basically just be burnt to death. So so that just shows like how things how devastating things could be. So what we've observed so far are just things that are happening within minutes to hours, like pyroclastic flows. But volcanic eruptions could trigger things that we don't usually associate with, like the 2018 eruption in Indonesia as well. It triggers a tsunami, and I think a lot of Malaysians would know about that as well, yes, hopefully. And then like the ash falls from it as well. You could see like this is from Guatemala as well. So this is a Gulf resort before the eruption, and it shows that with the pyroclastic flow, with all of the ash fall, just devastate this Gulf resort. And yeah, I think during the eruption of Agong itself as well, a lot of flights are being cancelled due to the risk of ash getting into the jet engine. So there's risk linking with that as well. And in the long term, there's actually climate effects as well. So this is based on the data collected by Hansen, and it's based on the 1991 eruptions of Pinatubo and other volcanoes around that period of time as well. So this vertical line shows it's 1991, and you can see that the average temperature, I mean, the normalized temperature over here, it's somewhere around 0 degrees. But after the eruption, you could see that there's a global cooling of about 0.3 degrees, like after the eruption. So in a way, volcanic eruptions could trigger global cooling, but that's just for short scale. It doesn't mean that we should have more volcanic eruptions so that we could prevent global warming. That's definitely not true. And so with all of these, I think yeah, it's the 1800s of the eruptions in Krakatoa as well. That's the main cause of the year without summer, but that's 1800s. So most of us don't know, but I think that's the eruption that that inspires Scream, I think. Yeah, that inspires Scream, the art by Edvard Munch. So yeah, here's just another slide just to show you the other uses of INSAR and SO2 spectrometers. So if you're interested, like, what are the uses of these besides looking at volcanoes? So you can look at earthquakes. So because earthquakes means that there's surface displacement on the surface. So you can measure things before the earthquake and after the earthquake to understand how much displacement has occurred during the earthquake. And you can measure like landslides as well, or land subsidence. So this map itself, it's the subsidence map of Jakarta. And you can see that the capital city, it's like subsiding up to a rate at about like 15 centimeters a year at the edge of this, like close to the sea over here. And I think a lot of us, I hope that a lot of us know that like Jakarta itself is sinking because of excessive groundwater extraction, and then like a lot of people are being displaced because of this as well. And this picture on the right shows the global mean of SO2 distribution, and what can we use SO2 spectrometer to understand like what's going on. So we could see like fossil fuel combustion source. So like if you're generating more more petrol and stuff like that, or if you're generating more energy, basically you have to burn fossil fuel and stuff like that. Or you could generate a lot of SO2 by smelting metals like iron, stuff like that. And you actually generate a lot of SO2 as well in the oil and gas industry. And yeah, so you could see that all of these are actually anthropogenic sources. And volcanoes are just part of these small aspect of it. So yeah, these are all I have to share. So for now, what we know so far is that basically volcano monitoring provides us a better understanding of volcanic eruption, and it helps us to forecast volcanic eruptions as well, to prevent further casualties or death of people. And infrared SO2 gas emissions can be used to understand magma properties. And by using thermodynamic models, we can help us to understand things and understand data that we don't have as well. And what we know so far is that the presence of volatile would make a magma much more compressible. And if a magma is highly compressible, it means that the surface deformation would be muted. And that means that we may underestimate how much magma is being intruded into the magma reservoir. And I'm not sure if there's anyone keen in this chat, but basically here are some sources that you could look around or play around with. So that's the COMET. You can get INSAR data from COMET or the ARIA JPL. We could get SO2 gas emission data as well from this website. And yeah, that's all from me. And feel free to connect with me on Twitter. And thank you.
Right, thanks, Stanley. Cool talk. If you could just close your screen share. You know, you were talking about, you summarized that understanding magma properties will, using all this monitoring data and satellite data will help you understand, or understand when the volcano might erupt. But you know, we saw a volcano erupted in New Zealand in December 2019, and it killed 5 people. And 2019 is just like a few months ago. So what went wrong there? Was monitoring not enough?
Well, so being able to monitor volcanoes itself, it's important, definitely. And I would say that I'm not an expert in this particular volcano, White Island, but based on my understanding is that because the magma reservoir itself is very shallow, so there's a lot of so things are very volatile over there itself, and then because it's so shallow, it's reaching the amount. It's so shallow that there's water that's surrounding the magma reservoir. So if there's water interacting with the magma, like the water itself would directly evaporate, and when it evaporates, it would expand as well. So this is a phenomenon that's called phreatic eruption. So it includes the evaporation of rapid evaporation of water, and caused by magma heating. So you could imagine like a bottle of Coke, and then the bottle of Coke itself, Coca-Cola, it's quite stable itself. And then you could imagine that as a magma reservoir. And you know, like the Coke and Mentos experiment, right? If you add Mentos into the Coke, the Coke will actually like erupts. So you could imagine like the water as the Mentos. So if you add the Mentos into it, and things would just
right. So you're saying that water plus magma is bad news.
Yeah, because things. So basically it means that the water will evaporate very quickly, and that would like cause some cracks in the reservoir, and it would open up some pathway for the magma to come out.
Okay, cool. I have a question. What are the downsides of only using satellite data for monitoring volcanoes?
Yeah, that's a good question because first of all, satellite data can never, I don't think it would ever replace ground-based monitoring because it's much more accurate that way. And satellite techniques itself, they have their downsides. Like for example, if there's atmospheric turbulence, you can't really use like the radar waves you use. It's not really accurate because it would affect the waves that's going on over there. So you could say that if there's a lot of atmospheric content in the sky or in the troposphere, that would slows down or delays the wave that's reaching the Earth and reflects back again.
Yeah.
So things like uncertainties could affect satellite monitoring. Definitely.
Yeah. So you're saying that if there's a week of bad weather, that will affect the satellite data, and you might miss some sort of signal that the volcano is displacing?
Yeah, that's true because so the thing is, satellite data, they have to orbit around the Earth, or if you're a geosynchronous satellite, which means it's always at the same part of the Earth, you can have continuous data. But if it's orbiting around the Earth, it means that
Right.
you don't have continuous data, and there's temporal resolution, bad temporal resolution. So at the moment, like Sentinel-1, the satellite itself can collect data like every 12 days, depending on what region you're at. But some satellite can only collect data, especially the older ones can only collect data like every 30 plus days or about 60 days as well. And
Oh, wow.
you have to take into account like the data that you collect doesn't mean that the data itself is good as well. It may be caused by a lot of uncertainties or a lot of noise, stuff like that.
Yeah, that's true. So we have a next question from Instagram. So do you know of any volcanic studies being done in Malaysia, both East and West Malaysia?
Yeah, there's actually a few. And actually the volcanoes, I mean the extinct volcanoes that we know of in Malaysia are actually done like ages ago, I think like the 60s-ish. And so there are studies being done in volcanoes around Malaysia, but it's not really done completely, and it's just done like with a few data, things like that. And I think one of the better studied one is the Kuantan basalt. So there's actually some volcanic rocks in Kuantan.
Oh, right, interesting.
Yeah, but it's not really well studied because the main problem is that we don't have the need to study this because it's not a problem for us. So we don't have to care about the volcanoes because it doesn't affect our lifestyle.
Yeah, that's true.
There's a lack of studies or
And
research.
funding, that's the main issue.
Yeah.
Right, cool. Next question from Instagram as well.
Yep.
So how does one person study a volcano located deep under the ocean? Is there a way to monitor it?
Yeah, so as I've mentioned earlier with the satellite techniques that I've been using, so basically they use either radar waves or they use the waves that's being emitted by the sun. So you could look at things in different wavelength. But if it's underwater, like if it's and the volcanoes would be like really deep, so basically there's no light or waves they could measure with. So what you could use is by simulating waves as well. So in this case, you could use like sonar. So it's like the way you the way you emit waves, like when you do mammogram and you use ultrasound, and that's just being applied to monitoring volcanoes.
Yeah, so one really basic question. So how are volcanoes discovered? Is it possible that there are volcanoes we don't know about?
Definitely, yes. Especially like especially if what we thought are like just mountains, but it may be volcanoes in reality. And especially like if it's heavily vegetated and then there's no people going there, and then basically you don't really have any means to know if this is a volcano or not. But if you're there physically, and then if you're there, and if you're interested like collecting rocks and stuff like that, you could actually like say that, oh, this is a volcanic rock, so maybe there's a volcanic eruption around here or surrounding.
Right.
Yeah.
Is it possible to use thermal means to detect whether it's a volcano underneath?
Yes. Yeah, definitely. Wait, sorry. Thermal.
Yeah, just like measuring the heat coming out of
Temperature. Yeah.
ground. Yeah.
Yeah, definitely. So so one of the other satellite technique is using thermal imaging as well. Definitely. Yes. So things get like in a way hotter, then that means that it's quite likely for things to be happening.
Right. We have a question from Facebook from Julian. Do super active volcanoes emit more sulfur dioxide compared to less active ones?
So I would say it really depends on what is the primary melt or the primary magma is. So if the rock itself, if the magma itself has higher SO2 content in it, then definitely it would emit more SO2. But at the same time, if the magma itself has a lot of SO2, but if it's being scrubbed, or in this case, it's like before it's being emitted to the atmosphere, if the SO2 is like being trapped into the volcanic rocks, or if it's being scrubbed, is a term to mean that it's being removed from the magma itself, and that means that the initial amount of SO2 that's being trapped in the magma would not be observed in the atmosphere as well. So that's actually one of the problem as well we're facing.
Yeah, so that might give a bit of bias to your results that you see in your satellite data.
Yeah.
Cool. Now on to some more personal questions. So how do you get interested in studying volcanoes?
Yeah, it's quite interesting because considering there's no volcanoes in Malaysia.
Yeah.
The thing is that like throughout my childhood, or like just growing up basically, and then just looking at the news, it's just quite sad to see like our neighbor Indonesia or the Philippines or just around the world, they have to suffer through this. And I think with all of these technological means, I think there's a good way that we could exploit these data. And the way I get interested in this is because it's actually based on the INSAR image itself. So when I was in year 3, and then I was taking a volcanology course, and then I just saw this image about these rainbow fringes, and I was like, this is interesting. And then like, how do we actually use like satellite data to measure all of these volcanic activities? And I was thinking like, how can I get into this field, and why isn't there more people talking about this? Because it's a really cool thing to do, and these data and measurements itself are really useful as well. But unfortunately, not a lot of people are exploiting this data, I think. So yeah, I think that's the way I get interested into volcanoes, especially the INSAR rainbow fringes. Yeah.
Oh, so you were like, oh, it's so colorful. Let's study that.
Yeah, but I would say that my personality itself is that I really like nature itself as well. And then I don't like seeing people die. And basically, I'm afraid of blood. So one of the main reasons I don't go into the medicine field as well.
So in your, have you been to any volcanoes?
I've not seen any erupting volcanoes, definitely not. But the dormant volcanoes, yes, I did. So it's just basically looking at rocks, basically.
Rocks. I love how you you say, oh, all geologists have rocks in your room. I was laughing nonstop.
Yeah, I mean, we collect things like this is interesting, I guess.
What's that?
So well, these are just quartz, but
okay.
Yeah, but just interesting and beautiful things, I guess.
Okay, I have one question. What is your favorite volcano?
My favorite volcano, it's quite tough, but personally, I think I would say Argon volcano, because that's my first research project. that I've done. And yeah, that's my master's project as well, which I've completed last year. So yeah, that volcano is my first volcano that I've learned in much more detail, and with the satellite techniques as well. So I think, yeah, my favorite volcano would be Argon volcano, and it's so close to home. And
Oh
it's,
yeah, that's true. You should visit it one day if it's safe.
yeah, it's such a shame. Like Bali's so close, but I've never been there. So yeah.
Well, neither have I. Okay, one last like technical questions about volcanoes. So, in your personal opinion, do you think the direct hazards are more dangerous or more deadly than the indirect hazards? So, for those, just to explain a bit more in context, so direct hazard means what I meant is like the volcanic gases during eruption, the ballistics,
Yeah.
as well as the avalanches, and indirect hazards meaning like climate change, atmospheric effects, acid rain, which leads to famine and diseases, because all the crops are buried by ash or eruptive materials, basically. So which
Yeah,
is more?
I think it depends on the risks and hazards surrounding the volcano, and there's actually like a huge study about this as well to understand like the economics behind the economics and the social, the socials behind the like volcanic eruptions as well. So if there's a lot of people staying around the volcano, then definitely the direct risks are quite huge, especially like volcanoes around Indonesia, because I think it was in our primary school, we learned that a lot of Indonesian farmers live beside volcanoes because the soil are so fertile. Things like, so yes, the direct exposure to volcanic eruptions are quite huge, definitely. But that depends on the risk, like how much people are staying around the volcanoes. But I would say that the indirect risk itself is quite huge as well, because that depends on how huge the eruption is. So like the 1883 eruption of Krakatoa or Tambora. Sorry. So either one of those huge volcanic eruption, it basically caused global cooling, and then it was the year without summer as well. So a lot of crops died, and a lot of people died from famine. And then even if you're not living around the volcanic area, like a lot of people died in Europe just because of there's no sun, and then you can't yield crops with that. That's a huge problem. And I think it's 1700s of 1773 eruption of Laki in Iceland. I think that was a huge cause of a lot of death. So I think there's not a lot of people died from direct exposure to the volcanic eruption, but a lot of people died from indirect exposure because their kettles, they die, and there's no meat for them to eat, and then a lot of crops died as well. So yeah, basically dying from famine.
Yeah, it was quite interesting when you mentioned that there are people who want to live next to a volcano due to the fertile soils. That was quite interesting, actually.
Yeah. So the thing is that so basically these people, they have to consider the risk between living beside a volcano, like if it's going to help their daily lives, or would they want to take the risk. So yeah, it largely depends if people want to take the risk or not. Because if you're selling like rice, I mean, definitely you have to staying by the volcano itself is pretty good, because you can have good rice. So yeah, I think it depends on the personal. Yeah.
Cool. Right. So one last question: what do you want to do after your PhD?
Tough question. So personally, I think I would like to stay on in academia, or if possible, probably like in observatories as well. And yeah, just to help improve our understanding for volcanoes, and not necessarily volcanoes as well. Like, probably we could try to understand like how satellite data could help our daily lives as well. Like, could measure land subsidence and so on and so forth, and probably like how we could use satellite techniques to understand urban expansion and things like that as well.
Cool. So we know now that Stanley is a hardcore volcano fan, and he would like to stay on the volcano line for quite some time. Right. I think that's all the questions we have today. So thank you everyone who joined us today. We have our next speaker is Xu Yao. So she's pursuing her PhD in cellular nanoscience, and she's looking at the mechanics of motor proteins in cells at a nanoscale. And for more updates regarding future Research Insider series, like our Facebook page, MBIOS and 100 Scientists of Malaysia. And thank you guys. See you next Saturday. And thank you, Stanley, for speaking to us about volcanoes and your passion for it.
Yeah, and thank you for having me as well. And thank you everyone for tuning in.
Okay, bye.
All right, thanks. Bye.